It is a superb particle finding. Physicists have actually detected a cosmic neutrino with the highest energy ever measured, and thus presented experts with a full-blown mystery for while the almost massless elementary particle at 220 head electron volts has 22 trillion times the energy of an electron. We know neither where it comes from, nor what has given it its incredible energy to unlock the wondrous particle world of the cosmos. You sometimes have to go to the bottom of the sea, or to be more precise, to the bottom of the Mediterranean Sea, because this is the location of the Kilnum 3-net Neutrino Observatory, which consists of the ARCA and ORCA telescopes. And while ARCA is located at a depth of 3,500 m off the beaches of Sicily, ORCA was installed 2,450 m below the water surface off the French coast. In detail, the components use optical sensors to observe the so-called TROV radiation, which is produced by the interaction of neutrinos and water molecules, and ARCA has now succeeded in detecting an extreme particle that exceeded even the wildest expectations of scientists. But before we go into this exciting discovery in more detail, we should first clarify a much more fundamental question. What exactly is a neutrino? Well, neutrinos are basically the most common elementary particles of all, but at the same time they are also the most mysterious. Every second you watch our video, 100 trillion of these tiny particles race through your body at almost the speed of light, without you even noticing. The Earth and its inhabitants are bombarded by neutrinos day and night from all directions, yet there are very few signs of them in spite of all. Since the fundamental building blocks of matter are held together by electromagnetic forces within them, a neutrino reacts only to the weak nuclear force, and thus to the force that holds the atomic nucleus together. However, this force only acts in the immediate vicinity of the nucleus, which after all makes up just 0.001% of the atomic volume. For a neutrino to react at all, it must collide with precisely this tiny fraction of the matter, but even then, it may still be that nothing happens at all given this complicated starting point. Steel, lead, and even diamond are not obstacles for the so-called ghost particles. It's not especially surprising that the ghost particles were only discovered on paper for a long time, but to understand this, we need to go back in time to 1930 and examine the issue that scientists were dealing with in the field of atomic nucleus research at the time. Specifically, the experts were trying to develop an equation that would explain how an atomic nucleus decays during radioactive radiation, and according to the laws of physics, the energy of the particles released after decay must be exactly the same as the energy previously stored in the nucleus. However, the measurements revealed that this was not the case, and that some of the energy always just vanished. Austrian physicist Wolfgang Pauli did something evil according to his own statements and added a new particle to his equation. That compensated for the energy loss Poe noted in his diary today. "I did something evil. I proposed a particle that cannot be detected." This is actually something a theorist should never do today. However, we know that the Austrian guilty conscience was unfounded. In fact, the existence of his particle was to be experimentally proven, a quarter of a century later, how the ghost particle became reality. But how do you prove the existence of a particle that hardly interacts with matter? Well, with the help of radioactive beta decay, which occurs, for example, in nuclear explosions, or in a nuclear reactor. In this process, a neutron transforms into a proton by emitting the electron and thus its negative charge, but at the same time so goes the assumption an anti-neutrino must also be created, and if this anti-neutrino encounters a proton, it triggers a change in charge the proton. Thus Beck becomes a neutron, and the anti-neutrino becomes a positron, and it was precisely this so-called inverse beta decay that opened up completely new possibilities for scientists in the 1950s. As soon as the positron meets an electron, the two mutually annihilate, creating a tiny flash of light that can be detected by highly sensitive photodetectors, and since the entire highly complex process only takes place when antineutrino are also involved. This indirect proof would ultimately also prove their existence by the same token. The reverse conclusion is that where anti-neutrinos exist, neutrinos must also exist, and indeed in 1956, Project Poltergeist was to provide the first indirect proof. of neutrinos in this way carried out on the grounds of the Savannah River nuclear power plant. In the U.S. state of South Carolina, the experiment was based on 3 steel tanks, each filled with over 1,000 L of a water cadmium chloride solution. And while the nuclear reactor provided a steady supply of trillions of anti-neutrino per second, the 110 photodetectors in the walls of each tank were able to capture the telltale mini flashes of light, the most energetic neutrino of all time today. However, we know that neutrinos are not only produced by nuclear decay in a sophisticated nuclear reactor apparatus, they are also produced by natural processes. Accordingly, cosmic neutrinos are released by supernovae or active galactic nuclei, for example, and although these neutrinos are particularly rich in energy, they are rarely captured, and even then only by large detectors such as the IceCube Neutrino Observatory at the South Pole. This is unfortunate to say the least, because these ghostly particles from space are considered special cosmic messengers that can provide us with unique information about the most energetic phenomena in the universe, as well as unique insights into the outer reaches of space. The most energetic neutrino known to date had an energy of around 10 electron volts. To put this into perspective, as previously mentioned, the Kilometer 3 Net Observatory has now detected a full-fledged energy monster that surpasses the previous record by a factor of 22. Although the observatory's construction is still ongoing, it is already performing an excellent job of detecting the most energetic cosmic neutrinos. Physicists measure the energies of elementary particles in electron volts, where the prefix PAA means 1 with 15 zeros, so 1 million times 1 billion. The sea's water masses serve as a natural detector tank for Kilometer 3 Net, which uses spherical photosensors to record the faint light flashes produced by neutrinos and their secondary particles colliding with water molecules. The signal received by Arc-E originated from a muon with an energy of 120 electron volts. This muon had raced almost horizontally through the detector field and produced such a strong Jove light that the nearest photodetectors were oversaturated. And to put this discovery into perspective, we have to remember that muons typically arise when extremely energetic neutrinos collide with atoms. However, since the muon was very energetic and also came from an almost horizontal direction, it must have been created by the interaction of a neutrino of even higher energy in the vicinity of the detector. And as already mentioned, according to the experts, this neutrino was traveling at an incredible 220 electron volts for an elementary particle that is incredibly high, or to be more precise, almost as high as the energy of a hailstone hitting the Earth's surface at a speed of 50 km/h. Why the record-breaking neutrino is so mysterious. In the course of this, the scientists were not only richer for the most energetic neutrino of all time, but also for the proof that neutrinos of such high energies actually exist in nature. For the experts, the discovery marks the beginning of a new chapter in neutrino astronomy, which is all the more remarkable given that the Kilometer 3 responsible for it has not even been completed yet, while ARCA is designed to comprise 230 measuring units anchored to the sea floor, each consisting of 18 photodetectors, suspended one above the other. Only 10% of the measuring field was operational at the time of the record observation. Despite all justified euphoria, the scientists cannot avoid pointing out another not insignificant fact: where the cosmic extreme neutrinos came from is still completely unclear at this point. In time, it had much more energy than anyone would have expected, and although the researchers were able to narrow down its original celestial location, the comparison with potential sources such as quasars, supernovae, and gamma-ray bursts did not lead to a direct match. The same applied to the search for lower-energy neutrinos that may have the same origin. But what about the background of the energy monster? Well, in this regard, the experts point out that we could all also be dealing with the result of a so-called cosmogenic neutrino production. That is the result of a process in which neutrinos are produced by the interaction of cosmic rays with extragalactic background light, or the cosmic microwave background so far. However, no such cosmogenic neutrino has been detected, and researchers are now hoping that Kilometer 3 Net will catch more neutrinos with comparably high energies. Then the search, supported by classical telescopes, could help to reveal their origin, and thus reveal even more about the fascinating spectacles of the universe. And now we'll tell you how you'll never have to miss a new video from us again. Just select the thumbs up button. And to keep informed about the most recent news, subscribe right away. We'll see you soon.